Okay, good morning, everybody. So a reminder that we're going to have our second midterm on Wednesday, a week from today. And continuing, so in the previous class, we looked at the matched Z transform. We said in the impulse invariance, we took the inverse Laplace of the filter. We sampled the filter. Then we get h of z from the sampled impulse response. In the matched Z transform, both the poles and the zeros are mapped according to the formula, where the poles and zeros are mapped to the exponential of s multiplied by t. So just to finish the matched Z transform, I'm going to just run the simulation and show you the results of the matched Z transform filter. Okay, so this is the results of the matched Z transform filter. This is our analog filter, our digital filter, and this is when you put the two filters together. And you can see when we added the two filters together, what do we notice?
They're pretty close.
They're very close, but why are they different? Because of aliasing. So keep in mind, even with the matched Z transform, there is an aliasing. Yeah, this is the bandpass filter example that we've done at the end of the class. Okay, so with that, we're ready to go through the third technique or the third method. So let me just put this matched filter example. Matched Z transform filter example. Okay. So the third technique that we can use to design our digital filter is called bilinear transformation. As we've seen, both the impulse invariance and the matched Z transform suffer from aliasing. And therefore, not only they distort the filter, but also they do not enable us to design, for instance, a high-pass filter. So therefore, we need another technique for converting the analog filter into a digital filter. And this technique is called bilinear transformation. So what we want to do in the bilinear transformation is the following. I want to be able to take the continuous frequency, and when it is equal to a zero, when I am at a very low frequency, I want to map this to omega equal to a zero. And when I am at a very high frequency, what is the highest frequency in the continuous time domain? Infinity. When omega goes to infinity, I want the filter to map to an omega that is equal to the highest frequency in the discrete time, which is equal to up high. Together? So therefore, the transformation that is going to give me this is given by this. S equal to over t multiplied by z minus 1 divided by z plus 1. And we'll see how this works in a minute. So what we What I'm saying is that if you were to design a filter, an analog filter, then replace S with this formula, 2 over T, Z minus Z minus 1 over Z plus 1, then your filter that goes from 0 to infinity is going to be transformed into a filter that goes only from 0 to up high. What does that mean? First of all, from this, we can write Z as equal to 1 plus T over 2 multiplied by S divided by 1 minus T over 2 multiplied by S. Now, what we're saying is the following. So I'm going to be plotting the filter that we're going to be designing in the continuous time domain. So this is H of omega, H continuous of omega. And this is the filter in the discrete time domain. This is H of omega. And this is our omega. So let's see what we're doing. So I have a low-pass filter that I designed. Chebyshev, Butterworth, elliptical filter, whatever filter we design. So this is the filter. Now what I want to do, I want to be able to take this filter that goes all the way to infinity and transform it such that it only spans the 0 to pi. So this is my lowest frequency, this is my highest frequency, which is up high. And the way we're going to do it is we're going to have a mapping that will look something like this. What is this going to map? It's going to map W to omega. What does that mean? If I have a filter like this and I'm able to map W to omega using the blue curve there, then I can see how the filter is going to look like in the discrete time domain by just taking points here, projecting it on W, and this is probably exaggerated in a bad way. Let me do it. Projecting it on W, so that is going to correspond to this point here. So if I have A, B, C, D, this is going to be the point B, this is point A, and then this point C is going to go and get mapped to this frequency here, so this is going to be point C. This is point D, and so on and so forth. I keep mapping these frequencies. Eventually, at infinity, this is going to map to frequency that is equal to a pi. Does that make sense? I should have made this like going this way, but it's fine. The idea should be clear. So if I'm mapping the filter, and I have a mapping between W and omega that's given by this blue curve that I have there, then at any frequency, at this frequency, this is omega 1. The amplitude of the filter is B. Omega 1 is mapped to W1 is mapped to omega 1. This is omega 1. The magnitude is going to equal to a B. Can everybody see it? Clear? Now what's not clear is why I made it this. just make a small correction. So this shape is the same as this shape, except that this goes from 0 to infinity. This goes from 0 to up high. Why? Because the mapping between W and omega is such that when W is infinity, is going to map to omega that is equal to up high. Any questions? Clear? Make sense?
I mean, we used to do this just manually when we transform from omega to big omega to small omega, right?
We never done this before. I mean, this is a new, the bilinear transformation. We never used this before. Usually, when we transform omega to W, we say omega is equal to W multiplied by T.
Yes.
What we've been doing so far is that omega is equal to W multiplied by T. Now, what we're saying, no, we're going to replace it so that it is transformed using this curve. We're going to relate it to omega by T in a second. Together? You guys take engineering drawing? Like projection and how this will project if you were, or if you look at an object, the front, the sides. They used to tell it. Graphics, yes. Okay. So let's see how this thing works. So what we said is the following. We said that S is equal to 2 over T multiplied by Z minus 1 over Z plus 1. So what we're claiming is this transformation is going to do all this magic. And we're going to try to explain how this all works. I can write this as 2 over T multiplied by 1 minus Z to the power negative 1 divided by 1 plus Z to the negative 1. Okay, now I'm interested in S along the j omega axis. So S is equal to j omega. This is going to equal to 2 over T equal to, 2 over T multiplied by 1 minus, I can write Z as e to negative j omega divided by 1 plus e to negative j omega. Together? Okay. Now, what I can do, what do we usually do when we have something like this? And 1 plus exponential over 1 minus exponential. The first thing comes to mind is I'm going to take half the angle here, half the angle at half the phase at the top, half the phase at the denominator. And we see this so many times. So I can take negative j omega over 2. And if I take negative e to j omega over 2 as a common factor from here, the 1 will be e to positive j omega over 2 plus, minus e to negative j omega over 2. Agree? Nothing changed. If I multiply them back, it's going to give me 1 minus e to j omega, which is the original formula. I'm going to do the same thing in the denominator. I'm going to take e to negative j omega over 2 multiplied by e to j omega over 2 plus e to negative j omega over 2. Okay. What can we do next? This is going to give me 2 over t, and this will cancel with this. And what is this going to equal to? sine or a cosine. It's a sine. This is going to equal to 2 multiplied by j multiplied by a sine of omega over 2. And the denominator is going to equal to 2 multiplied by cosine omega over 2. Make sense? These are added, so they're going to give me a cosine minus going to give me a sine, j multiplied by 2 multiplied by j by a sine. Okay, so therefore, I can cancel the 2 with the 2, I can cancel the j with the j, and I can write this as double. The j here.
Ah, okay.
Yeah, a different color. Okay. So I can write this as W is equal to 2 over T. And what is a sine over a cosine?
Tangent.
Tangent of omega over 2. So that formula that started with the S equal 2 over T, Z minus 1 over Z plus 1 is the same as this transformation. They're equivalent. It's going to map omega or W and omega using W equal 2 over T, tangent of omega over 2. Now we can also multiply by T over 2. This is going to equal to tangent of omega over 2, and therefore omega is going to equal to 2 tan inverse of W multiplied by T over 2. So I can write W in terms of omega or omega in terms of W. Both are equivalent. Now let's see what this graph will look like if I were to plot omega versus W using this formula that we just developed. So when W is equal to a 0, omega is going to equal to a 0. So we are at this point. When W is equal to infinity, what is omega going to equal to? When W is infinity, what is the angle that gives me, that has a tangent that is infinity? Pi over 2. So what is omega going to equal to? A pi. So when I am at infinity, omega is going to equal to a pi. Again, because pi over 2, the tangent pi over 2 is equal to infinity. So at this point, at infinity, omega is equal to infinity. When omega is equal to a pi, W is equal to infinity. And between them, the curve is going to look something like this. So if I take a point, for instance, when omega is equal to pi over 2, this is going to correspond to W, that is equal to 2 over T. Together? Everybody? And therefore, if I were to plot the curve of omega versus W, it's going to look something like this. And we can, show this also in MATLAB quickly. And again, this is the plot of omega versus W. Okay. So what do we notice about this plot? So let's make some observation here before we move on. Put this to the side here. So if we look here, when the frequency W is very small, when W is much smaller than 2 over T, what does the mapping look like?
Linear.
Very, very linear, very good. For low frequencies, and that is omega or W is much smaller than 2 over T. And 2 over T, what is this equal to? 2 multiplied by the sampling frequency. Then the tangent inverse of W multiplied by T divided by 2 is going to equal to W T divided by 2. And therefore, omega is just going to equal to W multiplied by T. Does that make sense, everybody? So looking here, when omega t or omega t over 2 is very small, the tangent is going to equal to the angle. Where was the formula? The one on the page before. And therefore, when the angle is very small, the tangent is almost equal to the angle. And therefore, omega is just going to equal to W multiplied by T, which is what we're used to. That's how we transform from W to omega. Now for the frequency, when the frequency becomes very large, when W is much larger than 2 over T, which is 2 multiplied by Fs, what's going to happen to the frequency? The frequency scale is going to get distorted. Together? And another way of saying that, we're going to say the frequency scale is warped significantly. So again, up to this point, we have a linear region, and therefore we're happy. That's what we like to have. But then outside of this range, all this frequency is going to map into this very tiny frequency. So therefore, all the frequency are going to be distorted. Make sense? Everybody? Here is linear. If I take a frequency, another frequency double, they're going to be doubled here. Here, if I take a frequency doublet, if I look at the transformation, it's not doubled. Make sense? Okay. So in that region, we're going to have a very wide frequency range for W that is going to map into a narrow frequency range for omega. So therefore, based on this, I'm going to make another observation, which is that bilinear transformation avoids aliasing at the expense of what? Distortion. At the expense of distortion. The range here is linear, but outside it's not. Therefore, the shape is going to be distorted at the expense. It is, yes, at the expense of linearity of the transformation, which results into distortion. And another way to say it is compressing the high frequency range. Is that clear, everybody? Makes sense? So again, looking back at what we started with, we're going to be able to design this filter from this filter. This is what the transformation, if I do, I'm going to be able to transform this filter to this filter. However, within the very small frequency, this transformation is fine, it's linear. Outside of this small region, I have to take all this region and compress it into this very tiny region. And therefore, it's going to distort the shape of the filter.
So the curve, the right-hand side of the curve, so that's like e to the negative x or something like that. Like what is defining that curve? What is defining that green curve?
It's
Like, you had a function for it.
This is the one we just
it's
did.
omega equals 2.
This is this one.
Omega 2. It's just flipped over.
This is the curve of W versus omega, which is this curve of omega versus W.
Just flip across the
Just
edge.
flip.
You just look at that.
Make sense? Okay. A flipped. So if I were to take this and just flip it like this, it's going to be this curve here. Okay. So therefore, if we're going to use this method, what we're going to have to do is we have to correct for this distortion that is going to happen at high frequencies. And the way we do that is we're going to correct for the warping that's going to happen because of this transformation. And to do that, we're going to pre-warp the pass band and stop band frequency. Okay. So what we're going to do, if the desired frequencies are omega C and omega stop, what we're going to do when we design the filter, we're going to design a filter for omega C hat, which is going to equal to 2 over T tangent of omega C multiplied by T divided by 2. And we're going to use omega stop hat, that is 2 over T tangent of omega stop T divided by 2. What does that mean? I'm going to try to correct for the distortion. What is the distortion going to do? It's going to compress the two frequencies, these high frequencies. It's going to compress them like this. So what I'm going to do, I'm going to make them even farther apart. So after they're compressed, they still give me the shape that I want. Does that make sense? What we're doing with this pre-warping? So again, if I have frequencies here, these frequencies are going to be compressed here. So what I'm going to do, I'm going to come here and re-warp them. So after they're warped, after they went through the warp, I have the frequencies that I really want to design the filter for. Okay. So therefore, we can put the design steps for the filter, and then we'll do an example and see how we do it. So the first step, when we design the filter, we're going to re-warp pass band and stop band specification. Using the formula that we just had here. The second step, we're going to design our continuous filter using the pre-warped frequencies. And the third step, we're going to apply bilinear transformation. Which is very lengthy. And from the bilinear transformation, we're going to get h of z from the filter, replacing s with 2 over t, z minus 1 divided by z plus 1. Next, we can set the gain. And then we can implement. We can have the difference equation that will implement the filter. Okay. Is that clear, everybody? Okay, so let's do an example on the calculations. Again, some of the calculations is not as much fun, but the good thing, you can always use MATLAB if you know what you're doing. Okay, so we have a filter that we want to design. And this filter, the specifications are given by the following. I want omega cutoff, which is equal to 2 pi multiplied by 2k. And I want omega stop, which is 2 pi multiplied by 3k. And I want an attenuation that is 12 dB. So this is the effective filter that I want to design the digital filter to do. Okay. So omega cutoff is equal to 2 pi multiplied by 2000 radian per second. And omega stop is equal to 2 pi multiplied by 3000 radian per second. And alpha is equal to 12 dB. And the sampling frequency is equal to 12 kilohertz. Okay, so we're going to just follow the steps that we laid out. The first step, we have to pre-warp the frequencies. So I'm going to calculate omega c hat, that is equal to 2 over t, 2 over t, which is 2 over 1 over 12,000, multiplied by tangent of omega cutoff, which is 2 pi, multiplied by 2,000, multiplied by t, which is 1 over 12,000, and divided by 2. And if I calculate this is going to count to equal 13,856 radian per second. What was the original frequency? It was, this frequency is 12,560. It's going to be bigger, yes. And the same thing, we're going to do the same thing. Omega stop is currently equal 18,840 radian per second. So this is, if I multiply it with the pi, this is the value. I'm going to do the same thing. I'm going to calculate omega stop hat 2 over t tangent of omega stop multiplied by t divided by 2, and is going to come to equal 24,000 radian per second. Together? Everybody? So what we have here is we have, this is the original, or this is the filter that we're trying to design. And instead, we're going to be designing a filter such that omega c is going to equal to 13,856 and omega stop is going to equal to 24,000. Why? Because after we take it through the bilinear transformation, this is going to get warped. After it's warped, it's going to look like this. Make sense? Okay. So the next step, now that we have the frequencies, we can determine the filter order. And since this is a Butterworth filter, we want 10 log 10 of 1 plus omega stop hat over omega cutoff to the power of 2 multiplied by n to be greater than or equal to a 12, greater than alpha, which is 12 dB.
They're both hat, right?
Yeah, they're both hat. And therefore, n is going to equal to a 3. So it has to be a third order filter. N is equal to 3. Okay. What is the next step? We're going to go to the table and get the filter from the table. So from tables, we know what the continuous filter is going to look like. If it's a third order, it's going to be 1 over s cubed plus 2s squared plus 2s plus 1. What do we have to do now? Unnormalize. So I'm going to replace s with s over 2 pi multiplied by 2000, which is the omega cutoff. And this is going to give me hc of s that is equal to 2 pi multiplied by 20,000 by 2000 cubed divided by s cubed plus 25,132 s squared plus 315,827,341 s plus 1.9844 times 10 to the power of 12. Where did this numerator come from? Because we're going to replace this with s over 2 pi cubed. We multiply numerator, denominator to get rid of it. Okay. Next step, we're going to apply bilinear transformation. And to do that, we're going to replacing s with 2 over t multiplied by z minus 1 divided by z plus 1. And this is going to equal to 2 multiplied by the 12,000, which is going to be 24,000, z minus 1 divided by z plus 1. Okay. So, therefore, we can write h of z, and I'm just going to put a constant here, even though there was another constant, but we're going to sum them all together in one constant, k. And then we're going to have sc cube, which is 24,000 cube multiplied by z minus 1 over z plus 1 cube plus 25,132 multiplied by 24,000 squared multiplied by z minus 1, z plus 1 squared, plus, this is continuing here, 315,827,341 multiplied by z minus 1 over z plus 1 plus 1.9844 multiplied by 10 to 12. Okay. What do we do with this? We simplify it.
Should there be by the 315,827,341 at 24,000?
Yes, there should be. Okay. So simplifying this, if you spend a few minutes simplifying it, you're going to get h of z, that is z cubed minus 0.965 z squared plus 0.58 z minus 0.10601. And believe it or not, this innocent looking h of z came from that formula. Okay, the next step is we're going to set the DC gain. And if I want the DC gain to equal to a 1, what do we do?
1 equals H1.
Yes.
Z equals 1.
We want h of 1 to equal to a 1. And therefore, we can calculate the value of k. And k is going to be 0.06385. And therefore, now we can write our difference equation. Y of n is going to equal to 0.965 y of n minus 1 minus 0.58 y of n minus 2, etc. Together, everybody? Now, of course, we could have done all this in MATLAB. Using this line.
Makes it worth the license right there.
Where this 1 over 3 is the 2 pi multiplied by 2,000 divided by 12,000. Omega cutoff, this is going to be pi over 3, and therefore the 1 over 3 is this part. Make sense? Okay. So let's run this impulse invariance, and then we're going to see what we can do to make this transformation easier. Oh, sorry, I ran the wrong one. Okay, so this is our example. We didn't do the Chebyshev, so we're gonna just get rid of this for now. Okay. So this is our Butterworth, the normalized, and this is our digital filter. And for this filter, so you can see what is the 3 dB of this filter. Omega cutoff, if you look at negative 3 dB, it's equal to 2,000. And at 3,000, I wanted the 12 attenuation, and I'm getting a negative 15 attenuation. Yeah. Okay. There's no aliasing, yes. Okay. Now, we said that we looked at the design. I mean, apparently the transformation, although it looks very simple here because we did not go through all the math of simplification, but you can see how this is really can be made better or simpler to calculate. So therefore, what we're going to look at next is an easier way to do bilinear transformation. Let me make sure it is easier. Okay. So given SC of S, that is equal to 1 over B sub n S to the n plus B sub n minus 1 S to the n minus 1 plus B0. And given S equal to C multiplied by Z minus 1 divided by Z plus 1, we can calculate H of Z. That is going to equal to Z plus 1 to the power of n divided by D0 Z to the n plus D1 Z to the n minus 1 all the way to the n. So given the normalized filter that we got when we first designed when we start designing the filter and know the filter order, I want to be able to go from H of S to H of Z. This is what I want, my digital filter. So we're going to find an easier way to find H of Z from H of S. And to do that, we're going to represent the denominator of H of Z, or we're going to calculate the denominator of H of Z as the matrix D equal Q sub n multiplied by U B sub hat, where D is equal to D0, D1, all the way to Dn, and all this transpose. And this is going to equal to Qn and Qn is given by this. This is the binomial coefficient in 0, 1, 1, 1, and 1, all the way to n, and we're going to calculate A, B, C, and X.
So is that and choose n?
Yeah. And then we have B hat, which is B0, B1C, B2C squared, all the way to Bn, C to the power of n, transpose.
So I'm sorry, is the row CX is on the very next one, or is that on the last one?
The row
Row
of
that has CX in Q.
this one?
Yeah.
Yeah, it's. I'll explain what it is. Yeah, but this is one row. This is one row. This is one row. One row.
N is the order of filter?
Yes. So this matrix is going to be an n plus 1 multiplied by an n plus 1 square matrix. And what else? And x is equal to c minus a minus b. And n choose x or n choose r is equal to n vectorial divided by n minus r vectorial r vectorial.
It's easier.
C? I'll say what it is. Oh, there is two C's.
No, but this is easier.
Oh, this is easier?
Yeah. No.
Really?
I don't know. You said it.
Oh, because it's a matrix, you can use MATLAB.
Okay.
No, this is supposed to be easier.
I guess if n's big.
No, probably I'm not going to do that, but if you like to volunteer and do that, go back to the example we've done and try to simplify it.
Yeah.
And then you're going to realize, like, okay, there must be a better way. There's no way they...
How do you get A, B, and C?
I'll explain. We'll do an example. But nevertheless, any entry is equal to C minus A minus B. So this is populated. All the other entries are calculated like this. This minus this minus this. And I calculate this minus this minus this minus this minus this. Okay. So again, what is it we have here? This is the h of z. This is the denominator we're trying to calculate. This comes directly from the h of s. I just have to multiply it by this c is different than this c. Nobody should be confused. Is the voice very low when I go to the board? Okay, I'll try to stay here as much as I can. Okay, so the only thing should be clear that this C is different than the other C. Okay. Now what is this C, which is here? This C is if h of s is unnormalized, then C is equal to 2 over T. If h of SC of S is normalized, then C is equal to 2 over T multiplied by 1 over omega C hat. Sounds good? Okay. So let's see how we apply all this. So we're going to go back to our example.
Can you go back to the previous page real quick?
And this is the C that is from the S equation. S equals C, Z over Z.
You know what I'm going to do? I'm going to make this a D. D. So there's only one C now. And that C is this one. C, C.
What about I see C times the quantity?
This one?
Nope. Up.
Like
That's-
for that,
Is it the same C from the S equation?
the S equals C, C minus 1, C plus 1.
No, this C, oh,
Is that the same C from the
yeah,
down low?
this is the same C. as-
Okay.
There's only one C.
Oh, yeah, that makes sense. I'm good.
Okay. Okay, so let's go back our previous example and apply the simpler method of getting h of z. So we calculated the normalized filter. SC of S was 1 over S cubed plus 2S squared plus 2S plus 1. So therefore, from this, I know B0 is 1, B1 is 2, B2 is 2, and B3 is equal to a 1. Okay, so the first thing, we're going to calculate our C, and C is going to equal to 2 over T. Since this is the normalized, it's going to be 2 over T multiplied 1 over omega C hat, which is going to equal to 2 multiplied by 12,000, which is 1 over T, divided by omega C hat, which was 13,856. And this is going to equal to 1.732, which is going to equal to square root of a 3. Okay, so according to the formula, we're going to calculate the B vector, or B hat, which is going to equal to 1 multiply, and then 2 multiplied by square root of 3, which is the C, 2 multiplied by square root of 3 squared, and then 1 multiplied by square root of 3 cubed. Is that clear?
Yeah.
Everybody? Okay. Then we're gonna calculate the Q. What is the dimension of Q gonna be?
3 by 3 or
4
4 by 4?
by 4. And the first, according to how we introduced it, N0, the first column is defined, and the first row is defined. So this is going to be, I'm going to have a number here that's going to come from 3, 0, which is going to equal to 3 vectorial over 3 vectorial multiplied by 0 vectorial, which is a 1. And the rest of the elements are going to be just 1, 1, 1. And then we're going to have 3 choose 1, which is going to be 3 vectorial over 3 minus 1 vectorial, 1 vectorial. And this is going to equal to a 3. It's going to be 3 times 2 times 1 over 2 times 1. You're going to cancel it, it's going to get a 3. And then we're going to get another 3. And this is going to come from 3 choose 2, which is going to be 3 vectorial over 3 minus 2 vectorial multiplied by 2 vectorial. And then finally we're going to get a 1 that's going to come from 3 choose 3 together? Okay. So this is populated from the expression. Now we have to populate the rest of the matrix, and we're going to use that formula that we had to populate it. So each element x is going to equal the element to its left minus the element above and the one to its right. So what should go here? 3 minus 1 minus 1, 1. What should go here?
-1.
How do you know where I'm pointing? -1. What should go here? -3. Very good. 3 minus a 3 minus 1, -1, -1, a 3, -1, 1, and -1. Is that clear, everybody? So again, let's just take one of these and show you how it's calculated. This is a 1 minus 1 minus 1. Actually, that's not the best example to give. Okay. So therefore, now we can calculate the D is going to equal to Q multiplied by B hat. We can multiply the two matrices together, and this is going to give me a 15.66, negative 15.12, 9.12, and negative 1.66. And therefore, h of z is going to equal to a constant multiplied by z plus 1 cube divided by 15.66 z cube minus 15.12 z squared plus 9.12 z minus 1.66.
Isn't that D transposed?
Yeah.
So what's this called?
I mean, that's bilinear transformation, just an easier.
This recipe here seems very. Some guy had to come up with it. What is it? It just doesn't seem. It doesn't seem logical to me.
I mean, it's not intuitive. It's not intuitive, but you can try it and it works. I mean, I'm sure there's a proof to it.
Yeah,
I mean,
Like what it just thought it didn't have a name.
I mean, the person I'm sure who done it, the method does not have. It's not known by a name.
Okay.
Okay. So therefore, k multiplied by z plus 1 cube, z cube minus 0.96 z squared plus 0.58 z minus 0.106, which is similar to what we've got in the previous example. Any questions? Okay, we still have 4 minutes. So we're going to do another example. Okay, so this example, we're going to do a Chebyshev filter. A Chebyshev type 1 using bilinear transformation. And we are given the sampling frequency is 12 kilohertz. Omega cutoff is the same as the previous example, 2000. And omega stop, 3000. And we are allowing a ripple of 1 dB. And alpha is equal to 12 dB. So if we were to plot the filter that we want, so this is 1 dB. This is 2 pi multiplied by 2000. And at 2 pi multiplied by 3000, this is a 12 dB. Okay. What is the first step? Pre-warp. And since we already pre-warped them and they're the same as the one before, you're going to get omega c hat that is equal to 13,856. And omega stop hat that is equal to 24,000. Okay, we're going to determine the filter order. We want 10 log 10 of 1 plus epsilon squared Tn squared of omega stop hat over omega cutoff hat to be greater than or equal to a 12. And why don't we do this? Why don't I ask you to finish it? Would anybody finish it by Monday?
Well, it's in the homework, so. We're gonna have to do something.
Well, you know, but before you do the homework, finish studying this. Okay, we're gonna get n equal to 3. Looks like you guys do not want to do it. I'm hearing hesitation. Okay, let's just finish it. I know we're running out of time. Okay, 2 over omega c hat is going to be the same thing, square root of 3. And then we're going to have b hat that is equal to 0.491. I mean, just keep in mind that when we calculate the b hat, this is not the like we take the b0 first, b1, b2, b3. They're not in the order of the polynomial. Okay. And D is going to be calculated from a similar Q matrix. So again, once you calculate the Q matrix, it will be valid for any filter order, for any filter of the same order.
Isn't that Q, not D?
Which one?
He's doing the bullet.
Yeah, I'm just going to do the multiplication. Okay, and we're going to get h of z. That is going to be k multiplied by z plus 1 cube divided by 10.7 z cubed minus 14.9 z squared plus 11.95 z minus 3.8, and h of z is going to equal to 0.0455 multiplied by z plus 1 cube divided by z cubed minus 1.38 z squared plus 1.1 z minus 0.35. And this is such that it has a unity DC gain. H of 1 is going to equal to a 1. Now also, we could have done all this work using MATLAB, using Cheppy 1. This is the filter order 3. This is R. This is 1/3. This is order. This is R. And this is the normalized frequency, which was the 2 pi multiplied by 2,000 divided by 12,000. Does that make sense? And this is going to equal to 1/3 pi. So this is the 1/3. MATLAB tells you, like, just give me what multiplies by pi. Okay, perfect. Any questions?
Where did the 1 dB ripple go when you figured out the Chevy shadow?
In the epsilon.